Hello, I'm Jared France.
And I'm Jason Handerhan.
And I'm Vera Lowe.
And we're going to share with you some information about state diagrams and Markovian queues on behalf of IOE 419. So let's first look at what a Markovian queue is. A Markov process is a stochastic process in which the conditional probability of being in any state at some future time, given past and present states, equals the probability of being in the state in the future, given only being in the present state. In other words, past history of a system does not provide any information needed to predict future states. In other words, suppose that we have a checkout line. We can mathematically represent this by using Poisson arrivals and exponentially distributed service times. We could also represent visually a Markovian queue using something called a state transition diagram, pictured here. This diagram shows the first 5 states of a system. You can see the dots at the end going off to infinity. The arrows on top, indicated by lambda and pointing right, represent the rate at which the state of the system increases. Say the rate at which a customer comes to a cashier to check out. The arrows on the bottom, indicated by mu and pointing left, represent the rate at which the system will decrease its state. Say the rate at which the cashier can check out customers. State diagrams help visualize the mathematical relationships between state probabilities and arrival and service rates.
So now let's discuss how to mathematically model a queuing system. We'll start by beginning to derive the Chapman-Kolmogorov equations. We'll start by going over some of the notation we need. Lambda n of t is the Poisson arrival rate with n people in the system at time t. Mu n of t is the service rate with n people in the system at time t. And p n of t is the probability of n people being in the system at time t. Equation 1 here states that the probability of being in state 0 with no one in the system a very short time from now is equal to the probability that the system is in state 0 now and no customer arrives, plus the probability that there is one customer in the system and that person finishes his or her service during the very short time. The second equation states that the probability that the system is in state I a very short time from now is equal to the sum of the probability that the system is in state I minus 1 now and there is one arrival during the very short time, plus the probability that the system is in state I right now and there are no arrivals or service completions during the short interval time, and the probability that the system is in state I plus 1 right now and there is one service completion during the short interval. So the Chapman, if we bring from those two equations, equation 1 and 2, if we bring pi of t to the left-hand side and divide by delta t and then take the limit as delta t approaches 0, we can obtain the Chapman-Kolmogorov equations. These equations provide the rate at which the probability of being in any state changes, as a function of time for any state of a Markovian queue, assuming that we have potentially an infinite number of states. So from here, let's discuss the steady state balance equations. First, we need to assume both arrival and service rates do not depend on time to estimate the long run average performance of the system. In the steady state, dp naught t over dt equals 0, and the change of pi of t with respect to time is also equal to 0. From that, we can rewrite the Chapman-Kolmogorov equations and write for equation 1 that 0 equals negative lambda 0 p naught p0 plus mu 1 p1. And we could also rewrite the second equation in the same way. So from solving 1 and 2 for p0, p1, p2, etc., it can be shown that the probability in being state j is the product of the lambda i's from I equals 0 to j minus 1 over the product of mu i's from I equals 1 to j multiplied by the probability of being in state 0.
There are two other approaches to calculate state probabilities in steady state. They utilize the state transition diagram shown earlier. The first is by isolating a particular state and setting the rates in to that state equal to the rates out of that state. In this case, for state J, the rates in would be lambda J minus 1 and mu J plus 1. The rates out of state J would be mu J and lambda J. We can also look at the space between the states. Here we can set equal the rate to the right and the rate to the left. In this case, J times the probability in state J equals mu J plus 1 times the probability in state J plus 1. This also results in the same steady state balance equations. From the steady state balance equations and the fact that sum of the probabilities of being in each state is 1, the key performance measures of the system can be computed, where L is the average number of entities in the system, W is the average time by an entity spent in the system, WQ is the average time spent waiting for service by each entity, and L of Q is the average queue length waiting for service. So here is a quick example of Markovian state probability calculations. Here we're given the arrival rates of lambda 0, lambda 1, and lambda 2, all of which equals to 1, as well as the service rates of mu1, mu2, and mu3, as shown on the screen. We're also given the probability of being in state 0, and that is 0.4. Now we need to calculate probability in state 1, state 2, and state 3. Using the equations shown earlier, we can find that the probability of being in state 1 is 0.2, and probability of being in state 2 is 0.0667, and for state 3 we have a probability of 0.033.
So some further applications of using this basic model is an MM1 queue, which has one server. It has Poisson arrivals and exponentially distributed service times. You can also have an MM1 queue with a restricted queue length, and you can have an MMS queue where you have S identical servers in a similar structure as before. You can also have an MM infinity queue with infinite servers, and you can also analyze queues with waiting and no waiting. So we thank you so much for watching. We hope that you enjoyed a brief overview of Markovian state probabilities, and you can see our references here. Thank you so much.